In the previous two videos, we introduced the phasor representation of current in an AC circuit, and we figured out the voltage phasors for resistors and inductors. Now we're going to figure out the voltage phasor for capacitors, and this completes our basic phasor analysis toolkit. So in the animation, we're looking at kind of the main goal of the video here. We see the rotating phasor diagram for a simple capacitor circuit on the left. So those are rotating vectors for the current phasor and capacitor voltage phasor. And then on the right, we see the actual sinusoidal functions that are generated from those phasors by taking their horizontal projections. So let's dive into the simple AC capacitor circuit and figure out how to pull this together from first principles. So this is the context for our derivation. We have a simple circuit that contains only an AC voltage source and a single capacitor, and there's a current flowing in this circuit, and that's going to be a sinusoidal current, but we just showed it moving clockwise at this particular moment in time. And like all these derivations, we say that that current function is I cosine omega t. In other words, we gave it a phase angle of 0, and we measure the phases of everything else with respect to the current function. So now to analyze this circuit, we're going to apply Kirchhoff's voltage law, or KVL for short. So we just traverse a complete loop around the circuit, keep track of all the voltage changes, and set it equal to 0. So we have this voltage step up V of t when we cross the power source, and then we go down the voltage across the capacitor. Now I've already replaced that with Q over C. Remember, the voltage across the plates of a capacitor depends on how much charge is on it, and that's given by Q over C. So we have V of t minus Q over C is equal to 0. Now the voltage of the power source is the same as the voltage drop across the capacitor. So we can go ahead and write that as V sub C. So the voltage across the capacitor as a function of time is just Q over C, where Q is also a function of time. The charge is changing on these plates. Now to get a grip on this capacitor voltage, we need to go back and relate it to the current function. So what we're going to do here is take a time derivative of both sides, since the time derivative of the charge gives us the current. So on the left-hand side, I'm showing a time derivative of the voltage on the capacitor. On the right-hand side, I just factored out the 1 over C and replaced the time derivative of Q with I. So now we can just multiply both sides by dt. So there's that. And now our plan is to integrate to find the capacitor voltage as a function of time. So we need to compute this integral, 1 over c times I dt, where remember I is a function of t given by that formula up at the top. So now we can sub in the details about our current function, and we're looking at the integral of 1 over c times I cosine omega t dt. Now the I over c is the spectator in that integral, and when we guess the antiderivative of cosine omega t, we get 1 over omega sine omega t. The 1 over omega occurs to take care of the chain rule. So there's our antiderivative. And if you're struggling with that chain rule a bit, just imagine differentiating this thing. The chain rule spits out an extra factor of omega, and it cancels the one we put in the denominator there. So that was the right thing to do. Now, the more skeptical among you might be asking, what about the plus arbitrary constant when we guess an antiderivative? And the answer to that is that we know the voltage across this capacitor must be a sinusoidal function. In other words, it's oscillating about a midline of 0, which makes the arbitrary additive constant 0. So we end up with a voltage function of I over omega c times sine omega t, and we're going to call that jumble of constants out in front the voltage amplitude. We call that capital V sub c. So we can write this as V sub c sine omega t, where V sub c is I over omega c. Now to make it easier to compare to the original current function, we need to express this thing in terms of a cosine instead of a sine. And you can do this by way of trig identities, or we can take a graphical approach, which is the method that I prefer. So here's a graph of the sine function and the cosine function. And what I'm indicating here is that you can get a sine function by shifting a cosine function by pi over 2 to the right. So that's sine omega t for our voltage across the capacitor. We can turn that into a cosine of omega t minus pi over 2. Remember, subtracting pi over 2 from the argument of a trig function, we'll shift it to the right. So this makes for an easy comparison to our current function. Remember, that has a phase angle of 0. I can immediately tell the voltage across the capacitor is phase shifted by pi over 2 relative to the current function. And in fact, it's lagging the current function by that quarter cycle pi over 2. And again, what does big V sub C stand for? That's I over omega C. So the next thing we're going to do here is try to get an Ohm's law style relationship for that voltage amplitude. Remember, Ohm's law says V equals IR. In other words, the voltage across the resistor is proportional to the current. And we're seeing the same thing here for the capacitor, except it's V equals I over omega C. So 1 over omega C is playing the role of R. And this thing gets a special name. It's called the capacitive reactance, normally notated as a capital X subscript C. And that's 1 over omega C. And for your physical intuition here, this thing is playing the role of resistance. It tells you how much effective resistance that capacitor creates in the circuit. Now note that this effective resistance is frequency dependent. So if omega is large, we get a really small reactance. This makes sense because changing the direction of current really rapidly means we never have much charge buildup on the capacitor, so it doesn't resist the flow of current as much. You can even say capacitors are transparent to high frequencies. And this is the basis for building a high-pass filter, but we'll get into that example in a later video. Similarly, we can imagine a very small omega, so a low-frequency current running through the circuit. That's going to give you a large capacitive reactance or a large effective resistance, because low frequency means the current isn't changing very fast. So that means a lot of charge can build up on the capacitor and result in a potential difference that opposes the flow of current. So now finally, we'll go ahead and write our voltage function in terms of the capacitive reactance. So we can say the voltage across the capacitor is I times X sub C, the capacitive reactance, times the cosine of omega t minus pi over 2, again, a negative pi over 2 phase shift relative to the current function. So we say this function is lagging the current function. So next we want to take a look at the phasor representation of this voltage function for the capacitor. So remember, in our phasor diagrams, we have everything rotating counterclockwise with an angular velocity of omega. And we see our current phasor there, this rotating vector with a magnitude of I. And then we see our voltage phasor for the capacitor with a magnitude of I times X sub C. And that's 90 degrees behind the direction of the current phasor. Now remember, the way that these phasors generate the actual sinusoidal functions we're talking about is that we take the horizontal projections of them to get the values on those sinusoidal curves. So starting with the horizontal projection of our current phasor, that's simply I times the cosine of omega t. Again, we call that a phase shift of 0. All phase shifts are in reference to the direction of that current phasor. So now we look at the horizontal projection for the voltage phasor for the capacitor. And the angle there is 90 degrees less than omega t. In other words, omega t minus pi over 2. So the projection is I times X sub C cosine omega t minus pi over 2. Again, that horizontal projection is exactly the voltage function that we solved for on the last slide. So now we can make an animation where these phasors are rotating with an angular velocity of omega, and we'll see how those horizontal projections produce the sinusoidal functions that the phasors represent. So in the animation, we can watch those horizontal projections of our current phasor and voltage phasor for the capacitor, and we generate points on the corresponding sinusoidal functions using the usual convention of rightward as positive and leftward as negative. And notice with that voltage phasor for the capacitor lagging the current phasor, we see that capacitor voltage reaching its maximum after the current reaches its maximum. It's always 90 degrees behind. In the next video, we put all our phasor analysis tools together. The voltage phasors for resistors, capacitors, and inductors, and we use them to solve the series LRC circuit. I'll post a link to that video at the upper left of the end screen, and I'll see you there.